Everyone, welcome to an introduction to smart contracts with Ethereum and Solidity. My name is Noah Hine, and I am going to be taking you through how you are going to write, test, and deploy your very first smart contract to the Ethereum platform. And given that this course is going to take about 45 minutes, that means that we are really taking you from zero to hero, and we will go over to the best of our abilities at a high level everything that you need to know, and you will actually have a working smart contract by the time that you end this tutorial. But that also means that there's going to be several things that you are left unequipped to deal with. And so without further ado, we'll go ahead and hop into what Foundry is, because Foundry is the smart contract development toolchain that we are going to be using throughout this entire course. And really every single lesson you will be using Foundry in one way or another. And Foundry manages our dependencies, it compiles our project for us, and it will also allow us to deploy our smart contracts to both our local machine and a test network, and it really streamlines the entire development of writing smart contracts, because instead of previous to Foundry, you would really have to hop back and forth between Solidity, which is the language that we use to actually write our smart contracts, and that is what gets compiled down into bytecode, and that is the code that is run on the Ethereum nodes that is actually executing the code that you've written. All of that happens in Solidity. And previously, you would need to bounce back and forth between, for example, like JavaScript or Python and Solidity to actually test your smart contracts. And Foundry is the first development toolchain that has embraced Solidity as like a first-class language that can be used for something that is something different than only writing smart contracts. So it will allow us to test our smart contracts writing the same Solidity language that we're using to actually write the source code that we want to test. And so without further ado, let's go ahead and hop into how do we install Foundry.
Foundry, as you can see here, is considered a smart contract development toolchain, which means that it allows you to easily create workflows for writing your contracts, deploying them, and testing them. To install Foundry, you can go to the Get Started tab. They will have different commands for all of the different platforms. For me, since I am on Mac, we can just copy this command, and then we can go over here and paste it, and that will install it. And then what we want to do is we can run Foundry up to install our project. And then wherever you want to create your project, you can run forge init, and I will call our project forge egghead. Here you can see that Forge has created a scaffold project for us. And what we will be really working on is out of the source and the test folders. Source is where your smart contracts will go. So you can see here that this is just an empty smart contract that needs to be filled out with functionality. And then there's a test contract that inherits the test contract that Forge gives us, along with some other nice functionality for writing tests that we will dig into. There's also this lib folder that we will not be making use of in this course, but is worth digging into as you level up in your smart contract writing skills. Whenever you import third-party libraries for various bits of functionality into Forge, they will go in your lib folder and you will import them in your smart contracts through there. All right, so to begin, we will open up our contract.sol file in our source folder. The first thing that you will notice is this very first line is a comment, and this SPDX license identifier is just what software license you would like your program to use. We will be keeping this as unlicensed since we are not planning to publish this. On our first line of code, you can see that we are declaring our Solidity compiler's version with pragma Solidity, and we are saying that we are going to grab a version greater than 0.8.13. And then we are declaring a contract whose name is contract. So let's go ahead. We will change contract to the number. And then we will declare a private variable of type uint, and we will just call that num. And so there's no value here. We are just creating the variable that we will assign a value to via the constructor. So our constructor will take another uint argument, and we will call this underscore num. And we will just set num is equal to underscore num. And this constructor will run whenever this contract is deployed, and then never again. The next thing that we'll want to make is a mutator function, and we will call this increment. And we will need to give it a visibility modifier of public, which means that anything or anyone has access to this. And so anyone will be able to increment our private variable called num through this public function. And so we will just set num is equal to +1. The next thing that we'll do is another function, and this will be decrement. And this will, again, be a public function. However, we also want, for this one, to take an argument of underscore num. And you can see this underscore syntax that we've used both in the decrement and in the constructor is not necessary, but is considered best practice whenever you are manipulating a variable that is contained within your smart contract. So since we are manipulating num, if you are going through a smart contract and you see this underscore, there should be a variable that doesn't have the prefix attached, that its state is kept in the smart contract itself. So for decrement, we will then just call num, and then we will take away whatever the value of underscore num is. The last thing that we're going to do is create a reader function, because currently we have no way to actually read the value. Since this is a private variable, we do not have access to it. And for this reader function, we will again make this a public, and then there is another modifier, and this is called view. And view just means that no state is going to change in this contract, and it will throw a compiler error if you attempt to change state in the contents of a view labeled function. And since we're going to be returning something, we need to declare the return type as well. And so it will be returns a uint. And so you can see here, we can just return num. Awesome. And this is the entirety of the smart contract that we will be using. However, you may notice that this on line 16 is potentially a bug, since everything in this contract is of type uint. We are just taking any number, an arbitrary argument, and taking it away from num. There is potential for underflow errors to occur here. And so we want to account for that. And so we will create a custom error, and we will call it unsafe decrement. And here what we can do is we will just wrap this in an if statement. So we could say if num minus underscore num is greater than 0, then we can go ahead and safely deduct the parameter num from our value of num. And if it wouldn't be greater than 0, then we don't want to do it. And what we'll do here is we will just call else, and we will use the keyword revert, which will abort the execution of this function, and it will revert any state that had changed. And so we will say revert unsafe decrement. And that will just throw this custom error that we established earlier. And now we can know that, hey, this will always be safe to do so, and it will throw an error should we perform a dangerous or unsafe decrement. All right, so here you can see that we are in our test folder, and we're looking in contract.t.sol. Here you can see it looks just like our other smart contract file where we declared the Solidity version. Here you can see that we are importing the test.sol smart contract, which we are inheriting on our contract test by using isTest. So this contract test has all of the functionality that the Forge standard library provides through this test smart contract. And here you can see it has a function called setup. Setup is run once at the beginning of each test suite, and so you can do any configuration that you need in this setup function. So to get that set up, we're going to need to import our contract.sol file. And then what we can do is with that imported, we can say that we've got a number contract, and we're going to put that in the variable number. And then in the setup, we can say that number is equal to a new number, and we'll declare 10 as the beginning variable there, or the beginning value for our smart contract. And now you can see if we run our file here, if we save it and then we open up a terminal and we run forge test, that everything is still running and we've got an OK. And you can see that we've got this test example. It will go through, Forge will go through every single function, and if it has a test prefix, it will test it and it will expect an assertion to be true here. So we can go ahead and really quickly check to make sure that everything is still working by making that fail. And now you can see that our test suite will fail. So with that, we can actually delete this test example function, and we'll go ahead and create a new function called test increment. And test increment should be a public function. And for this, what we want to do is we want to call the get number, because we want to track that. So we'll do number.getNum, and we'll store that in that contract number variable. And then we can call number.increment. And so now we can expect there to be a difference here between number.getNum, because that should return 11 now, and contract.num will be 10. So we can see if we do assert equality, and this will take two parameters and just compare the two. So we'll say we would expect contract num plus 1 to be equal to number.getNum. And we can go ahead and run that, make sure that all of this is working. And so we run forge test, and you can see, awesome, we are getting a passing test result. And so the next thing that we'll want to do is we'll want to test the decrement. And so we can just copy a lot of this, and we'll call this test decrement. And here we will actually want to pass in a number, since that's how our other decrement works. It doesn't just, it takes an argument. And so we'll call this an unsigned integer of type number, or an number of type unsigned integer. And we'll call this get num, and then we will call the decrement. So we'll do number.decrement, and then we will call num right there. And so here we can see if we do not minus 1, but minus num, should be number.getNum. And so we would expect this to work. However, whenever we run forge test, you can see that this actually doesn't work. And you can see that the reason is we're getting an unsafe decrement right here. And that is not great, but it does mean that our error is working. This unsafe decrement error is happening whenever we call a number. But why did that happen? You can see whenever Forge sees that you have put in a parameter for one of your functions, it will fuzz it for you. If you're not familiar with what fuzzing is, it just means that it is going to throw a bunch of different numbers into this function, and it's going to run it each time, and it's going to expect all of them to pass. And so you can see that it obviously did a number that was larger than 10. That would have caused some integer underflow, and so it reverted it. But that means our test failed. So in order to combat this, we have the ability to constrain the fuzzing numbers. And so we can call the VM is the virtual machine, and it has, it kind of
allows you to modify the runtime. And so we can say vm.assume, and we want to assume that our number is going to be smaller than whatever number.getNum is. And so now, whenever we run this test, you'll see that all of the numbers will be small enough and we won't run into that error again. And so here, if we run forge test, let's go ahead and make that bigger. You could see, okay, cool, we are getting 2 OKs. But, it's good to be able to test that if we made any breaking changes. So we want to actually have a negative test as well that makes sure that, hey, this is still failing whenever this vm.assume isn't there. And so what we'll do is we'll actually turn this comparison sign and we will flip it on its head. We want to say that, hey, the number is always going to be larger than whatever our current value is. And so if we do this, we should see that our test suite fails. Awesome. And you can see our test decrement, bad. Oh, and it also is complaining that we have the same thing twice. But you would see that it fails for the same reason that the other one did. But aside from the different names, we want to actually do this test fail. And if you add this fail right here, Forge will expect the assertion to fail. And so here, if we run this and we do forge test, you can see that all of our things are passing. And with that, we actually don't need to assert equality here because we are never getting to this line because this number.decrement is always going to be throwing an error. So we can remove that and see that forge test is still running and all of them are passing. And this is good, but it's actually not great to test that your contract just isn't working. And so we would actually like to get a little bit more specific because it's good to know that it's not working, but you want to know why it isn't working. So I would say generally that this test fail is a bit of an anti-pattern, but you're not always able to exactly pin down why it's failing. So this is kind of a stopgap solution. But what you really want to be doing is test, and we'll say cannot is typically the word that you would use. Cannot doesn't have any actual value. It's still just a regular test that's going to expect something to be true. But we'll say test cannot decrement larger numbers. And here we'll again uint num, and it will be a public contract. And here, it's going to be these exact 3 lines again. But what we actually want to do is we have this assumption here, but the VM has a lot of what Forge calls cheat codes. And so what we can actually do is we can expect it to revert. And so what this will do is it will say, hey, we expect the very next thing to cause something to revert. And it will also say, hey, what do we expect that revert to be? And so here we'll leave this blank to see what runs. And so if we open this up, we can see that if we run forge test, that we can see, ooh, that failed. And which one failed? Looks like the last one did. So the test cannot decrement larger numbers. And so we'll go ahead and copy this and we'll actually dig into this a little bit. And so we'll do forge test and we'll pass a flag here. And so you can do dash and then 4 V's, and this will add like a debugger or tracer to it. And then since we don't want to make things too noisy, we'll do match test, and then we'll pass in our test right here. And so here you can see that it only ran the one test, and we also attached a debugger here. And so you can see that we ran our setup successfully, cool. And then on this test, we got the number, it was 10. We made an assumption, and then we did another get number. And then whenever we did the expect revert, you can see the actual error here was an arithmetic under/overflow. And so here you can see that the reason went from our custom error to this. And so this arithmetic under overflow is really what's happening under the hood a little bit. And so what we actually want to do is we have access to that class of error. And so we'll say std error, and we'll call this an arithmetic error. And now we can see that whenever this passes, or whenever we run our test, again, you can see that, hey, it passes. And it's giving us some warnings about our unused variables because we're not actually using the contract num here. So we don't actually need to use that. We can assume that the number is going to be larger, and then we can know that this is going to revert. And so now we don't even want to do all of that. We want to test the entire suite right here. And so now whenever we run forge test, you can see that all of our things are passing. And here, the only other one, yeah, you can see that it's also saying that we are not using this. But like I said, this is a bit of an anti-pattern, so we will actually just remove that test entirely. And now, whenever we have an entire passing test suite with no warnings and no errors, and we know that our contract is both incrementing and decrementing and having a specific error that gets thrown whenever the decrement